Okay, today we're going to talk about radian measure, converting radians to degrees in the unit circle, polar coordinates, and applications of sinusoids. So, radians. It's a way of measuring angles essentially on a circle, and radians is equal to radius of the circle divided by, no, arc length. It's arc length divided by radius. So it's about essentially like thinking of central angles of a circle. And the easiest radius to divide by is 1, so we end up with this thing called the unit circle. It's a circle of radius 1. And the arc length along, since I'm dividing by radius, the arc length along the unit circle is always the same as the radian measure. So, if I have a circle of radius 1, the circumference is 2 pi. So radians is 2 pi. Would be equivalent to 360 degrees. So we end up with a conversion of 360 over 2 pi, which can simplify to 180 over pi. That would convert radians to degrees, or pi over 180 would convert degrees to radians. So what does this actually look like? Well, say I've got an angle here. Say it's 60 degrees. Okay? So 60 degrees, if I wanted to convert 60 degrees, if I want to convert to radians, that's pi over 180 degrees. That means my degrees will cancel, but that's a 1 and a 3, giving me a radian measure for 60 degrees of pi over 3. If I want the coordinates of this point, I essentially have a triangle in here with a hypotenuse of length 1. And I can either, if my calculator's in radian mode, I want to do radians. But if I want y and x, sine of 60, or pi over 3, equals 1 over, no, y over 1. If I type that sine of 60 into my calculator, that gives me my y coordinate. And that is square root of 3 over 2. Cosine of 60 degrees would give me my x coordinate, because over 1 doesn't really matter. Cosine of 60 is 1. If my calculator is in radian mode, that's sine of pi over 3. And you can see if you test it with your calculator that they are both the same, whether we do it. So the radians are another way of measuring an angle. They're end up being far more useful than degrees, the computation-wise. It's a lot easier because radian isn't really a unit. Okay, so that's radians. Well, we can think of graphing, like measuring something. Usually we measure it by how we mark it horizontally and vertically. Say I've got the point 2, 3. Another way of looking at it is what we call polar coordinates, where we measure it by, we usually look at the same, by a radius and an angle. So my coordinates look like this, r theta. Instead of having coordinates of 2, 3, we'll figure out what those coordinates are here in a second. By I know these sides of the right triangle, 2 and 3. So I know the sine of theta equals, well, first thing I probably need to do is find r. I do that by using the Pythagorean theorem. 2 squared plus 3 squared equals r squared. Square root, or 13 equals r squared. Square root of 13 equals r. So the sine is opposite over hypotenuse. To get my angle, I need to use the inverse sine. I suppose I also could have used the inverse tangent. Either way, I was going to need that. And I get 56.3. So my equivalent coordinates in polar are square root of 13, 56.3 degrees, or if I wanted it in radian, .98. Okay, so your angle can either be in degrees or radians. Um, an angle something like would look like this. Angles are measured from the positive x-axis going counterclockwise, always, unless they're negative. I'll give another example of this would be, I could do this, negative 430. So negative 430 is actually the same spot. If the radius is negative, I do something like go to 30 degrees and go 4 in the other direction. So it ends up actually being the same thing. Or the negative angle would go that way. Okay, so polar coordinates are just a way of going between them. So converting rectangular to polar, you have to do r sine. You figure out the radius with the Pythagorean theorem. Draw in the triangle here for your coordinates. Use inverse sine, cosine, or tangent to get the angle. If you have polar coordinates like this and want rectangular, well, I know 4. Draw in my triangle. I know this is 30 in there. So this side, y, that's sine of 30 equals y over 4, which means 4 sine 30 equals y, which that's 2. The thing about this, though, is it's in the negative direction, so I have to just assign the sign correctly. My y-coordinate is negative 2. My x-coordinate is I find with the cosine. And I get negative 3 point, ends up actually being 2 square root of 3 if we get an exact. And again, this is going in the negative direction. If I look at my angle, my thing is in the negative x's. My coordinates in rectangular are negative 2 square root of 3 and negative 2. So I'm converting back and forth using trig and Pythagorean theorem. Okay, that is polar coordinates. Now we're going to look at, and this here, oh yeah, let's look here for a second. This is our unit circle. Our unit circle is a very useful tool. It's got the x and y coordinates, and the cosine of whatever angle is the x coordinate. The sine of that angle is the y coordinate. The angles are given on this unit circle in both radians and degrees. So really important thing. You want the cosine of an angle, you can look at the unit circle. If the angle is on the unit circle, you can look at the unit circle and find the cosine by the x coordinate, the sine by the y coordinate. And so that was, knowing this unit circle was partly how I knew the sines and cosines of the last problem. So now finally we're going to go to the graphing of sinusoids. So periodic functions are functions that repeat, like the sine wave shown on the screen. Every 2 pi, it repeats. So between here and here, I have an identical. Or I could think of it as repeating from here to here. That's not labeled quite as well on the graph, but the period will usually be represented by capital T is 2 pi. So period, capital T, 2 pi. So let's look at some real life examples. So here I have the sine shown with a phase shift. A phase shift is a horizontal shift. This one is to the right, pi over 2. I know that because it's got a minus pi over 2 in the parentheses spot, or in the phase shift spot. So if I'm looking at this particular function here, I want to identify it. I know it has an amplitude of 2, because it's there. I know its period is 2 pi over b, or 2 pi over 3. I know that its phase shift, since it is factored out, is pi over 2, and its principal axis is 1. Those are very important things to note about the graphs of sines and cosines, being able to identify those things. So, let's look at a few realistic problems. A tank is filled with tap water. A tap at the base is opened and the tank drains in such a way that the height of the water in the tank h in meters after time t can be modeled and transformed by the equation y equals x squared. Find a model in the form h of t equals a t minus b squared using the following information. The initial height of the water is 65 meters. The tank is drained completely after 70 hours. Okay. So, hence find the water level after 30 hours. So, its initial height is 65. Tells me h of 0 equals 65. So 65 equals A, negative b squared. So, or ab squared if I simplify this. And the tank is completely drained. I know this information. So I need to use that information to find me a model. Okay? I can tell the tank is going to be fullest. Probably this looks parabolic. Should be something like that. So it's going to be empty at the bottom. The part, it's not going to refill, so it's going to look something like a parabola. When there's less pressure on it, it drains less quickly. So this means either A has to be 0 or B has to be 0. B is 70. Can also kind of think of that as B is the x-coordinate of my vertex, which definitely has to be 70. I don't know what I'm using for units there, but that's got to be 70. I then need to figure out A. 65 equals A times 70 squared. So I'll divide by 70 squared, and I get A equals 0.0133. So my function, h of t, equals 0.0133 t minus 70 squared. So b, h of 30 equals 0.0133 30 minus 70 squared. And that is h of 30 equals 21.2. They rounded way too much. I did not let my answer round. I got 21.2. I disagree with their answer. You should have kept at least three significant digits, 0.133. But I used the exact. Okay, this table shows the number of thousands of species of fish at the start of each year over 22 years. So, it says, why do numbers oscillate? And then find an appropriate sinusoidal model that fits. So why do they oscillate? Well, they go up and down as population and predators increase. Um, so to do this, we're going to use the graphing calculator. I guess that means it's time to start a new one. I don't want to save, and I'll start with a list in spreadsheets. Time. This one at least a 20. It might have went to 22. Need to go back and check my data. Went to 22. Okay, 11.7, 10.6, 10. 6, 11.7, 12. One 10.2, 10.2. Okay, so I've got my data entered. I need to add a page. Okay, I need to escape that. Data and statistics. We'll do time, population. Definitely looks to be oscillating. Menu, analyze, regression, show sinusoidal. And this becomes my sine function. So 1.00466. I've got it showing a lot of digits. I could drag it around until I can see the whole thing. That's my sine function. Let's look at find that fits the data. And so they got this. It had very close to 1. They definitely rounded some things off. Looking at the data, the highest value appeared to be 12, the lowest was 10. So they decided that the amplitude was 11. There seemed to be repeating. So they kind of did this by hand. I would recommend just using the graphing calculator. Okay. They looked at the graphs and said, oh, it's a sine. We shifted over. They decided that it was 11 at 1.5. Okay. So there's some kind of looks at it. This is very close. That's pretty close to what we end up getting. Okay. That is the applications. One last application that's not really in this book is beats. Beats are kind of a funny application from physics. And beats have to do with, so different notes produce different frequencies on a musical thing. So one of the easiest ones to know is A, the fundamental frequency of theirs that you usually tune to is what's called A440. And it is 440 hertz. Okay? Well, beats happen when we have notes of different periods. So you've got one at 440, say you've got one at 441. Okay? That means the period is slightly shorter for 441 because this is a frequency, not a period. What happens is the waves build together. When we get what this constructive interference, it's like the wave gets big, you just add them together. But where it's destructive, I've got a plus and a minus. So I've got essentially one wave up and another wave down. And when I add them together, another wave in the down part, when I add these two waves together, I get 0. Well, because they're not quite the same period, we get this constructive and destructive interference pattern that looks something like this. A lot of times we'll tune instruments by listening to the beats. When the beats go away, it means the frequencies have lined up. Okay? Which means they are the same frequency, the wavelengths are the same. That's a few applications to some of these functions.